Good morning. This is a summer school, so I prepared a somewhat eclectic, informal presentation, and I ask you to feel free to stop the show, ask questions, point out mistakes as we go. I think I have 2 times 45 minutes, so what I had in mind is, actually, you notice that the title is somewhat different, but the content is probably similar to what you expected. Dusty plasmas in the solar system. I will tell you a little bit about motivation. What exactly do I mean about dusty plasmas? I'll spend a couple minutes just to see how the physics would be different from plasma physics that you normally discuss. And then I go through a couple examples. Dust in magnetospheres. I understand that you know by now quite a bit about planetary magnetospheres. What dust can do, move around in a magnetosphere, get captured from the outside and can be thrown out from the inside. Actually, I don't think I have an example for capture, but I will show you transport and ejection of small particles from magnetospheres. And then in the second part, we move on to airless bodies like the moon or asteroids, comets. Of course, we are all very excited about the upcoming Rosetta mission. And since it's a heliospheric school, I would like to finish up with how dust moves around in the heliosphere coming from the outside, interstellar dust, and how can we identify that? And also nanodust from the sun thrown out or pushed away, traveling across large distances. So here is just a collection of things that you know. And I imagine you know this quote from Hannes Alfvén, that 99% of the visible matter in the universe is in plasma state at all scales. We could look at even at close to the Earth, at noctilucent clouds. Lightning discharges and so forth. But in fact, most of these places, the plasma is not pure, not only a collection of electrons and ions, but there are macroscopic particles. Huge molecules, tens of thousands and millions of large molecules. And the interesting part that the plasma physics is different because now we have a charge to mass ratio that is very small. And actually the charge on the dust particle is not quantized in a sense as it is for an ion, because it can carry millions of electrons or missing millions of electrons. Of course, quantized still in a sense that you can only change the charge by 1 electron unit. You cannot split an electron unless you are doing the Millikan experiment in undergraduate lab. This is the chart of the universe, the plasma universe. This is temperature in log scale, in kiloelectron volts, and the densities and the various regions that you could look. Solar wind, 10 eV or so, plasma densities of tens or a few. Certainly we know about comets that put a lot of dust. Certainly we know other reasons where there's a lot of dust in the solar wind. In the Earth's ionosphere, dust might or might not play a major role in the chemistry and the energetics. Flames is certainly one of the first systems where dust and the role of dust has been recognized. And it turns out that by now our friends who do fusion research worry about dust, born in situ or born by ion sputtering of the walls, and that's bad news for them. So all kinds of plasma physics is worry about dust particles. Of course, if you increase the temperatures and you go inside of a neutron star or our own star, then the role of dust is vanishing. So it's always a good start. Now it's online. You could look up the Encyclopedia Britannica. What is a plasma? It's a collection of positive and negative charges, about equal in number or density, forming an altogether neutrally charged distribution of matter. It is often called, isn't it, the fourth state. And it's unique in a way how collective motions and collective interactions emerge between the particles that make up the plasma. It's not a gas. There are long-range interactions, and you could support different type of waves, and you could do different type of things than what happens in a neutral gas. Now, things could get a little more interesting, even more interesting than plasma physics on its own, if you put in a macroscopic charge carrier that can absorb some of the electrons and the ions, and it forms its own Debye shield. Large distances, it remains hidden. But all of a sudden, if you are only look at electrons and ions, you think you have a non-neutral plasma. For example, because a lot of the electrons will be locked up on very massive particles, and they seem to be missing from the plasma. But they are not. is still charged neutral. But I looked up on massive particles that respond to things differently. And there is yet another level of complexity if you put enough dust that they communicate between themselves. They overlap, and the Debye spheres overlap, and they notice each other. And there is a long-range interaction between dust. And in that case, you could support waves in the dust medium. You could do instabilities on the dust and waves in the dust. And that, I will show you, is an incredible victory for plasma physics. And I'll tell you why in a sec. So, what are the pieces that go into these discussions? You could certainly think of a dusty plasma, like that would be the case in comets or planetary rings, where you have electrons and a whole bunch of ions, oxygen, ionized once, twice, right? All kinds of species, and possibly positively and negatively charged dust. You could also start with no plasma at all. Just shine dust on the surface of the moon or an asteroid, and all of a sudden you liberate electrons due to the photoelectric effect, and you leave behind a positively charged surface. Now we can have a good argument. Is this a plasma? Do you really have Debye shielding if you only have electrons? What sort of plasma is that? Well, it is a plasma, and Debye shielding turns out to be working just fine, and everything that you discussed in how plasma wall interaction would work would also work if you only have a photoelectric sheath, and I show you experiments that were done just a mile from here. Actually, there is also an even simpler setup. Start with neutral dust and have a lot of collisions. Through collisions, they exchange charges. The system remains neutral. You have the same amount of positive and negative charges, but they are carried on different dust particles. Turns out there is several tricks, like your size might tell me that you are preferred to be negatively charged. So for example, if you look at the plumes of a volcano, the upwind can separate small particles from big particles. The small particles, preferably, they like to steal electrons from the big guys. And due to drag, of course, they are entrained in the upwind much easier than the big fellows. So you are mechanically pushing them apart. If you separate charges, you build up an electric field. If you overcome the local breakdown potential, you make electrons loose and you make an avalanche. That's the lightning discharge. It's the same volcano during the day and at night, and you see these discharges that are generated by charge separation of dust particles in the upwind of the volcano. All right, so where is the new physics coming from? Certainly, if you think of everything that Plasma 101, if you took it, you start with gyro motion, single particle motion. What will be different? Well, certainly the spatial scales are different. If you think of the normal magnitude of magnetic fields in the planetary magnetosphere or in the solar wind, the gyro radius of a dust particle becomes enormous. Yeah, its mass compared to a proton is a factor of a huge 10 to the 10. There's enormous spatial scales that come to life. Dust moves much slower, and the time scales will be very different. And I try to convince you that there will be, new waves and instabilities that we could think about because dust is in the system. The way that dust couples into the plasma, first of all, that it becomes charged by collecting electrons and ions. The dust can either be a source or a sink or both. Yeah, if you shine light on it, it will emit electrons, or it can absorb electrons. If energetic enough electrons will come in, it can produce secondary electrons. It can change the chemistry, the energetics, everything in the plasma. So charging is an important step, but let's go back to a plasma wave. The only thing I believe that you have seen as a plasma waves is wiggly lines of potentials versus time, or electric fields versus time. This is a plasma wave, and you could see it. We downshifted everything to human scales. The wavelength is a centimeter. The frequencies are seconds. These are dust particles. This is a dust acoustic wave. This is a longitudinal wave. It was predicted by Rao and Shukla in 1990 and first observed at University of Iowa in 95. This is actually a photograph of high density and low density regions where dust particles accumulate, and then there is a lull, and there is a high, and there is a lull, and this whole thing is propagating. That's a dust acoustic wave on human scales. So the wavelength is upshifted, the frequencies are downshifted, and all of a sudden you could see a plasma wave. All right, so there is something else that is curious, and that is that you could make crystals out of the electrostatic interaction between the dust particles. If that is strong enough, you could almost, like in elementary school, you learned about how you form by freezing and melting things, you could form liquid and crystal. If I increase the electrostatic interaction with the particles and go into this regime that is easiest to achieve, it's called strongly coupled dusty plasmas. In dusty plasmas, the coupling is so strong between particles that the way that they energize, they minimize the energy of the system, they form a lattice. So there is such a thing as a dusty crystal or strongly coupled dusty plasmas. Typically, these experiments are hard in the laboratory because of gravities. Yeah? The crystal that you are generating in an RF sheath or a DC sheath would collapse under gravity. So these images are from the space station in microgravity environment. So let's spend a couple minutes. How do I figure out the charge? What sort of issues do I face? Here it is. Imagine that I will take the simplest possible system. I put a single grain into the plasma, and I figure out the flux of electrons and ions, and I follow the charge as it changes in time, and I argue at some point you will be in equilibrium. Once you are in equilibrium, the flux of electrons and ions must be the same. Initially, that's not the case, because even if they have the same temperature, electrons are 40 times more mobile than ions, a proton. Yeah, that's just the thermal speed. So initially, there is going to be a whole lot more electrons reaching the surface and starts charging the particle, the grain, negatively. As it charges negatively, the new electrons that are heading to the surface are somewhat slowed down. Hang on, buddy. You have a hard time getting here because I am building up a repulsive potential. As opposed to the ions, is hurry up. It's attractive to you. So the initially unbalanced fluxes will come into equilibrium by charging the grain negatively in a plasma. Of course, it could be more complicated. You could have, in addition to the collection of electrons and ions, energetic enough electrons to do secondaries and photoelectrons. But at equilibrium, all of this has to be add up to be 0. So let's do the simplest possible case. Imagine I have a single charge on the grain, and I have another particle coming in, and I try to figure out the cross-section for a collision, and that was probably an assignment for you either in E&M or in mechanics, and that is the Rutherford Scattering, 1/r potential, and you worked it out, and I can figure out that cross-section, integrate over a Maxwellian distribution, and I can tell you what will be then the flux of electrons and ions reaching the surface as a function of the densities of the electrons and the ions, the temperature of the electrons and the ions. And this is now the reduction of the electron flux. This is the surface potential of the grain with respect to 0 at infinity. And this is the enhancement. The potential is negative, so it's repulsive for the electrons. And there is a cross-section enhancement due to attraction of the ions. And if you want to solve this, you have to rely on a computer. Yeah, that's a transcendental equation. It's hard to solve. There is an exponential on one side, linear parts on the other side. But nothing would stop you to solve that on a computer. It turns out that the potential that you get to a large extent is independent of the size of the particle, because both of these currents are proportional to the surface area. And if you have a simple model, and we can argue about the validity, that the capacitance of an isolated dust particle is simply 4 pi epsilon naught, the vacuum dielectric constant times the radius. That's the surface potential. That would tell you the charge. Or an easier to remember set of units, I can tell you that the number of electrons on a micron-sized particle that has 1 volt is 700, missing or extra. So every 1 volt, every micron is 700 electrons. That's how the units work out. All right, so let's go to the lab. Let's start thinking if any of this would work out in the lab. And for the last decade or so, we have done a whole lot of plasma experiment. The reason I show you, it's cute, of course, because a flame is a dusty plasma, but it was done by the daughter of Wing Ip, who was one of our friends who started the physics of dusty plasmas, and she was about 10 years old at the time. So what is the simplest experiment you could imagine to measure charge on a particle? Imagine we have a a vacuum chamber, typically at pressures of 10 to minus 6, so the mean free path is quite large of the neutrals. We can have a filament that we run current and make it hot, so it will emit electrons. I can bias that filament against the wall, so it will spray electrons into the volume. And as I drop a dust particle from a salt shaker, it will fly through the volume of the plasma and fall into a Faraday cup where I measure the charge. That was the first set of experiments we have done here at the University of Colorado, and actually it happened since many other places. And the good news is, as a function of the size of the particle for a given potential difference between the filament and the wall, the charge that we measure is simply proportional to this. The charge that we measure, this is in units of millions of electrons. These are typically what is to have a cheap electronics and not to worry about noise. We drop big particles, like 100 micron size particles. So these are big, hefty charges, easy to measure. If you really work at it, you could measure 100 electrons at a time. We do that at the dust accelerator that you might or might not visit during your stay. So the charge that the particle will collect in the spray of electrons is simply proportional to its size. You could also ask the question, how does the charge going to change with the bias potential as a function of the energy of the electrons that would hit the particle? And at the beginning, it is proportional, and then something terrible happens. There is a deviation from, these are glass particles, and the blue dots are for graphite particles. There is a deviation from the simple linear relationship that you would expect. Something else turns on. This is now when the energies are high enough that you produce secondary electrons. So an incoming electron has the right amount of energy, or enough energy, that it will produce other electrons to leave. So that current actually is changing sign. Yeah, so the physics is changing as you are increasing the electron energy. You could also do it without a plasma if you invest in a high-quality quartz window, so it will let UV light across into your chamber. And at that time, we had a kilowatt mercury xenon arc lamp. That this is the energy as a function of the intensity as a function of wavelengths or energy. We shine light, drop dust particles, and we measure the charge. And that is the same physics in some sense, that the photons kick off electrons. And the smaller the work function of the material, the larger the charge you could measure. Okay? Yes, please. Yes. Let's go back to the very beginning. Yes, the question is this concern about an open system. That means, of course, that typically the electron and ion densities are not maintained because across the boundaries they are free to flow in. Or better yet, even if I look at the simplest possible picture and I put a little grain in a plasma, there is a horrible thing would happen that she's pointing out. I assume that's the question. If you wait long enough, the plasma will vanish. Because even at equilibrium, electrons and ions are coming to the surface. They are coming at the same rate, but they are still coming to the surface. So I'm missing a piece of physics. I didn't lie to you. I just prevented that level of discussion. So what has to happen then is, to help that problem, you have to recognize that at some point, electrons and ions can meet up on the surface, recombine, and make neutrals. But to maintain the plasma, then you need some other agent to ionize them again. For example, electron beam or photons coming into the system. On its own, it will not survive. The system is open. I need another energy source to maintain it. And I imagine that's your point. Very well taken. All right, so imagine, or hopefully I built up enough trust that if someone tells me the densities and the temperatures and the composition of the plasma, I can figure out the charge. And that's already good enough to do some interesting physics. And the first set of examples will be dust in magnetospheres. So, you might have seen the equation of the motion for a single charge particle. This would be the force due to a magnetic field. If there are electric fields present, you have to add that term. This is the piece that you would write down for electrons and ions. For a dust particle, of course, the charge is different, the mass is different, but the motion would be identical or similar to what you expect for an electron and ion. In addition, you will have to add gravity. I chose to write it down in a complicated form. If there would be no, it's a simple 1/r potential, you could stop here. Typically planets that we worry about, Jupiter and Saturn, and there are other terms, higher order terms in the gravitational potential. But this is the equation of the motion, and of course, based on a previous discussion, depending where you are and how fast you move, you could write down all the currents and figure out the charge, the instantaneous charge, and see what happens. Now, if you go and look at this equation in the limit of enormous charge-to-mass ratio, then of course these terms will dominate, and you are back to the adiabatic motion of electrons and ions, and dust can do that, as we will show you in a sec. Tiny, tiny dust particles really behave like light ions do. And of course, you are also familiar with the other limit. When the charge-to-mass ratio is vanishing, you have to get back to Kepler orbits. And of course, the nicest piece of physics is somewhere in between. You are very familiar with what happens with the gyro motion of small electrons and ions. You are very familiar with what happens in gravity alone. But when there is a balance between these forces, something interesting can happen. So first of all, this is actually from a homework I assigned, an MEV proton at the Earth launched at synchronous orbit with various pitch angles initially. So this guy would mirror at 20 degrees, this guy would mirror at 40 degrees. And I imagine that you are very familiar with the adiabatic constants. You know about the gyro motion, about magnetic field lines. You know about the bounce motion between the mirror points. And you know about the drift motion about the planet. Now, I would like to show this to you in a somewhat different picture. And I would like to have this discussion to keep it simple in 2D. So the particle motion that I will discuss actually has 90-degree pitch angle. So the problem is 2D. Okay, I will stay in the ecliptic plane or the equatorial plane of this planet. All right. And I choose a reference frame where all the drifts are taken out. So this is, I show you the particle motion in a mean motion frame. So and these are the particle sizes, 20, 40, and 80 nanometer. Saturn is a good case because the magnetic field is very well described as a centered aligned dipole. And I imagine that all particles, for the sake of argument, at the moment have minus 10 volt surface potential. And they all start at Kepler speeds. And this is inside the synchronous orbit. So a charge-to-mass ratio that is very large would have a standard gyro motion. That's a circle. Yeah? This particle is light enough. Its charge-to-mass ratio is high enough that it behaves exactly like an ion. It goes around and around the magnetic field line. Now I will start turning down the charge-to-mass ratio, make it smaller and smaller by making the particle bigger and bigger. So look what happens. This is a 40 nanometer, and then 80 nanometer gets the gyro motion gets bigger and bigger and gets distorted. And at some point it starts shrinking. And at some point it will settle into a 2-to-1 ellipse, which is a Kepler particle. That's how you transition from large charge-to-mass to small charge-to-mass ratio. Now you could recall your mechanics class and say this is a central force problem. Even adding the co-rotational electric field, that's still a central force problem. I could capture an angular momentum-like quantity that knows about the charge that is conserved. I can put that into an energy equation, and I get kind of an effective potential, an effective one-dimensional potential that would describe your radial motion. So here it is. This is the effective potential for this particle. So it will speed up and slow down and speed up. And this is the initial energy. That's the potential. So its velocity will be high in the middle, and it will simply oscillate. And if it's parabolic, then of course this is a simple harmonic motion. And if it gets far away from parabolic, then physics gets a little bit more complicated. It's an anharmonic oscillator, but it's nicely bound, and nothing unexpected happens. As you are keep decreasing the charge-to-mass ratio, that potential will open up or close up again, and you are back to the Kepler potential. And that's the one that you are familiar with, fixed angular momentum. What is the effective potential? So I will change nothing, but I will change this sign to a plus. Okay, a positively charged particle, and the same story. And here is the particle. Doesn't matter whether you're positive or negatively charged. For large enough charge to mass ratio, you just run about circles about the magnetic field lines. As I make the charge to mass ratio smaller and smaller, this gyro path gets bigger and bigger. Here is the potential. Here is the potential. Here is the potential. My God, that is non-confining. If you start a particle here, you will not keep it at Saturn. There's a leak. You are free to go. It's a non-confining potential. You have more energy than the barrier that would keep you in place. More energy in a sense that is including both the mechanical and the electromagnetic terms. And then you have to keep increasing all the way up to 120 nanometer when the potential will close up again, and you are back to the standard Kepler orbits. And of course, in the meantime, you have these weird trajectories at Saturn. So you say, this is crazy. I never heard anything like this before. And you are right, because it took till 92. This is Ulysses flying by Jupiter. That's how it got to this highly inclined orbit that it is following today. And there were two major discoveries. I will tell you both today. One is the stream particles, small particles running away from Jupiter, which is nuts. That's the biggest planet in the solar system. If anything, it should be a big vacuum cleaner. Now I'm telling you it's a big vacuum, a big dust source. It is throwing particles away at high speeds. The other one that we get to the end of today's discussions is the discovery of interstellar dust flying through the solar system. Both happened in 92 when Ulysses took the south turn at Jupiter. So here it is. What I'm showing you is time. There's impact rate. Ulysses had an impact ionization dust detector. We probably discussed that a little bit later today. When particle hits at high speeds, it makes a little cloud of electrons and ions. You could separate them with an electric field and collect the signal out of a multi-channel plate or an ion collector. That was a spinning spacecraft, so whenever Jupiter was in the field of view, or at least once in a while when Jupiter was in the field of view, you had this incredible increase in impact rates that appeared to be tiny, sub-micron, maybe 50 nanometer size particle, coming at you well over 100 kilometers per second. The reason I'm hesitant to tell you the speed and the mass, because there is no way we could have ever calibrated this instrument for this mass and speed range. All I can tell you that the signals are unusual, and they are consistent with what we believe these tiny, very fast particles will do. And of course, Galileo came by a little later. That is 94, and the streams are there as well. And if we imagine that we go to Fran or go to someone who could tell you about what is the plasma density, what's the temperature, I could start particles out of Io. Io, I know it's volcanic. It produces a lot of ash. And as Io goes around and around, I can try to figure out what happens if I solve F equals ma, dq dt is all the currents, and I just follow what happens with the particles. And that's an animation. That is the trajectory of Galileo, and in a second or so, Cassini will come by. This is the encounter of Cassini on its way to Saturn at Jupiter. Well, let's see if I can make this happen. No. You see a mouse somewhere? Ah, there we are. So here it is. Io goes around and around and around and around, and it is spewing little dust particles, ash particles, and some of them will escape at high speeds, and they will be picked up by the dust detector on Galileo close in. And actually, we have seen these streams on Cassini at Jupiter, and I will show you the second. Saturn works the same way. We have seen these stream particles out of the magnetosphere at Saturn. So one question, of course, half mv squared, there's a whole lot of energy. Where did they get it from? Pardon? Electrons will give you charge. I need energy. Close? Close? We all learned V cross B, that's a force, but it doesn't give you energy typically because the displacement and the force are at 90 degrees. So what do you need? An E field. There is an E field, the correlational electric field. That energy comes from moving a dust particle along the radially outward point, a positively charged particle, the radially outward pointing electric field. If you calculate that integral, E times Q times dl, that amount of energy is turned into the kinetic energy of the particle. It comes from the co-rotational electric field. So the next set of data I will show is Galileo. That is actually not the final plot, but these are the trajectories. The sun is kept. This is a strange system of coordinate system. The sun is kept to the right. These are the years and the loops and the color code. So this is projected down in the ecliptic plane, and the color code is the impact rate. The Galileo dust detector have seen almost identical to the one Ulysses was carrying. And notice something really weird, because if Io is the source, how come that we have really high intensity parts when we are far away? I expect that the closer you are, the higher the flux, and that was not always the case. And it turns out if you look at the timing of this thing, and Galileo took images of the surface on Io, some of that relates to big volcanic outbursts and resurfacing events. We didn't always catch a big outburst, but you came by orbit after orbit, and you see fresh material. I think it was reddish or whatever on the surface. And between two events, two encounters, you see a whole lot of new deposit on the surface. That must be that the volcano somewhere went off. And it is possible that the time dependence of the source itself would tell you how come that in 2000 we had this huge flux of stream particles when we were really far away. And in general, it looks kind of complicated until you do something different, and that's a victory for theory. You can imagine that Io goes around and around and around, and I will average out how the particles will escape over a long period of time. If I were to put down a curtain far away, what sort of patterns would I see on that curtain? And it turns out, because of the offset, how the plasma behaves at Jupiter, the particles will leave the system not azimuthally, in an azimuthally symmetric way. In fact, very few of them will fly towards the sun, and there are these enhancements in different directions, like in the morning and in the evening. And this is a prediction from '97, and that's the data that Galileo collected through 2002 at the time. So yes, it works. Not only does it work, but thus now gives you kind of a different take, that what you believe is the plasma model, it has to be consistent with the dust measurements. Because if I were to put back the Io plasma torus right at the center, and I forget about the tilt, and I do something wrong, even in the magnetic fields, or what I believe the plasma densities and temperatures are, this pattern wouldn't work out. So the dust allows me to kind of have a global view, trust but verify what our friends in the magnetospheric community would tell us. Yes? Some of it is pointing, some of it is that the dust didn't go that way. So there is a lot of nuances in these statements. One is I certainly have to fold in duty cycles, how much time the instrument was on, what is the amount of time it was pointing in the right direction. But to the best of our ability, this color code took care of that. Or to the best of our ability of my colleague Harald Kruger, that this is already taken out the standard stuff, the duty cycles, the pointing, the trajectory, and so forth. So this is now back to 2004. Time versus impact rate on our way approaching orbit insertion at Saturn. And the high-speed streams are there. They are somewhat punier than at Jupiter, and that is all right, because that's a somewhat punier magnetosphere. The gravitational electric field is weaker, but we do have sources. The rings could be a source. At the time, of course, we didn't know that Enceladus works to a large extent like Io at Jupiter, and whatever dust you see, it is probably at whatever small dust you see outside the main rings is probably coming from Enceladus. That is also an important source of plasma, an important source of dust. But by the way, if you want to come back and make an estimate how much dust Io should produce that I see these fluxes, How does that compare to the canonical number of a ton per second of plasma being produced? It's a tiny fraction. Probably a kilogram a second will do to match the amount of dust that I see in the dust detectors. All right, so I'm not quite sure if I'm breaching on my allotted time or not, but I have one more subject. 5 minutes, okay. All right, so maybe I bring up one more subject, which is hopefully interesting, and that is the rings of Saturn. And there is an amazing structure. It's incredibly well organized, and it's an incredible victory of our friends who do nothing else but gravity. You see these resonances of various moons, you see structures, and colleagues spend their life explaining the structures, and as time goes on, they are remarkably successful doing nothing else by gravity. Maybe when it gets a little hairy, then they have collisions between the particles that make up the moons. But things are incredibly well organized at small scales. And when Voyager took these images, and when Cassini took these images, things are nice and steady and as good as it goes until you take a closer look. And of course, these are images taken by Voyager. And this is an image on approach, and these dirty patches appear. What the heck? They don't have any right to be there. It's all gravity. And gravity certainly cannot do anything that is propagating in the radial direction. How on earth you get energy and angular momentum, and how, if everything is, all the forces are radial? How can you do that? Why are these black spotches appearing? And they were certainly dark on approach. And then you look back to the sun, and they were bright. That immediately tells you something. That the size of the scatterer is probably proportional or roughly in the same region where these images were taken in wavelengths, which is visible. So somewhere on the half micron size is the characteristic size of these particles. So they appear dark in backscatter and bright in forward scatter. So that's a bummer. We've never seen anything like this. They come and go. They appear in minutes. They run across enormous distances. And we had no clue what it is. In fact, famous colleagues of ours had no clue. This cannot be explained with the known laws of physics. That was in the von Karman auditorium. I wasn't there, but I have ear witnesses. And our friend Hannes Alfvén was there. Also, he was a character and says, be careful. There is a difference between the known laws of physics and the laws of physics known to you. So, what can I briefly tell you, and what sort of models do I have? By the way, I don't have an answer. I can just tell you where we are at and what we hope to learn as Cassini goes on. So these patches appear to be intermittent, and they come and go. The contrast in brightness is somewhere below 10%. The length is about 10,000 kilometers. The width typically is 2,000. They all appear too close to be synchronous. Some of them actually gets across the synchronous radius. The cadence of the Voyager images were 5 minutes apart. And we have real estate, pictures of real estate without spoke and with a fully evolved spoke from subsequent images. So the darn thing run across this huge distance in less than 5 minutes. They appear to be radially aligned. They appear to be new or fully radial in the morning terminator. I'll show you what that is. And then the picture is consistent that they shear away, and I will tell you what I mean about that. There has to be that the particles that make up these has to be submicron because of light scattering properties, and they remain either in the ring plane or very close to the ring plane. So people had a whole zoo of questions. Are they just realigned? There's some kind of a magic that we have elongated grains and they do something with our images. Is the plasma density and temperature anywhere enough to kind of have an electrostatic lofting or some electrostatic effect, and so forth? Why in the morning? What determines the frequency of their occurrence? And some of the ideas, I like to put them into these three categories. I'm not sure how valid this is. Some of them is kind of static and somehow has to do, the grains doing something like little compasses, they do some weird stuff in the ring plane. Or it is possible that we have a bunch of single particle trajectories and they do something funny. They all jump at the same time and they evolve somehow at the same time. But really, it has to do with single particle motion. Better yet, maybe there is some sort of a dusty plasma wave propagating in one way or the other. Maybe solitons, maybe some really interesting plasma physics that makes up the spokes. So I'm gonna talk to you just about that one, and then let's see what happens if I start a cloud in fully radial direction. The dotted line is the synchronous radius of Saturn. This is the inside of the B ring, and that's the outside of the B ring. I think it was like 1.9, 2.4, or 2 point something, 2.3. That's synchronous. If I look at big particles are on a horse race. The ones closer to the planet move faster. That's Kepler shear. So if you look at big particles, and that's the leading edge, the big particles simply show you how they shear away. Yeah, the ones closer in run ahead, the ones further out fall behind, and this front must be made out of big particles. And as time goes on, of course, the system is rotating this way. As time goes on, the shear gets larger and larger. Tiny particles are behaving like ions. They are stuck to field lines. They co-rotate. So a co-rotating particle will show up and always remain in the radial direction. Yeah? Those are the co-rotating particles. So depending what the size distribution is and how particles are born, that's the real estate a spokes can occupy. Somewhere between co-rotating and Kepler particles, this is the real estate that you can have. And some of it is promising. Some of it is promising because the shear, this kind of a shear, and better imaging later on would tell you, indeed, the size separation is such that the leading edge inside synchronous, because not all spokes run across the synchronous radius, but if you are inside synchronous, the leading edge is bigger particles. If you are outside synchronous, the trailing edge are made out of big particles. So imagine that I want a surface. Should stop about. All right. So maybe I'll take 5 minutes and then I'll start. I will shorten the second part. Imagine that I will have a sheet of paper and it is charged, and I see if I can lift off small particles from that just by charging it. So that is, you could work out, of course, how the charge density relates to the normal electric field. You could estimate the normal electric field by figuring out what the surface potential is divided by the Debye length. That would roughly give you the magnitude of the electric field. You could turn that into then plasma density and temperature, and that's how the numbers work out. The charge density on a surface will be proportional to the surface voltage with respect to 0 at infinity, and the square root of the electron over electron density versus temperature ratio. The probability of a ground to have a single charge, I would estimate that by simply multiplying its cross-section with the charge density. And you could turn that into a probability, and it turns out that most particles will remain uncharged, and the tiny fractions in the rings would have a single charge. In fact, that amount of charge that a particle will have on the surface is a tiny fraction what the charge it would have if it's alone in the plasma. Okay, so let's... how would lifting work then? Imagine that this is a surface. I have a plasma sheath. So up there is an undisturbed plasma. Here it's the region where I have a charge imbalance. That's the sheath. Because of all the charge that is missing from the surface or added to the surface, roughly lives in this region. There is an inward pointing electric field if this is negatively charged. So a negatively charged particle will feel an uplifting force. And you could say that the probability of get a liftoff is proportional to the probability that you have at least one charge. You should have at least one charge, otherwise these things would not work. That probability is proportional to a squared. Then you have to move across the sheath. If you start with a negative charge and you are in an ion sheath, it's very likely that you will catch an ion. You will lose your charge, even change the charge sign, then you fall back down. So I have to get across without losing my charge. That turns out to be proportional to the minus 3/2 power of the radius. This is your discharging time. So at the end of the day, the escape probability is going as a squared for small grains and falls down as 8 to the minus 3.5 for larger particles. So for a given plasma environment, there is a preferred size that you could lift off from the surface. So let's take a look what we expect at Saturn. I did my best. I did a literature search. I wrote down every number I could find that is relevant and came to the conclusion that the probability of having an electron is kind of small and depends on the plasma density. So if the plasma density is 0.01, 0.1, 1, 10, 100, and 1,000, these curves will tell you the probability of having a liftoff as a function of the particle size. The only reason I show it to tell you that to get liftoff, I need high plasma densities, and they are not available on the ring. So I need to look for something that at least once in a while would increase the plasma density by 1,000-fold. There is at least a transient plasma cloud with high plasma density. And people argued, our friends Greg Morfield and Chris Kurtz argued that you could do that if you have a big impact. Once in a while, large particles, half a meter size particles will hit the ring. They generate an impact plasma, and momentarily, until it expands, recombines, cools, and vanishes, makes a high plasma density. And look what happens if you generate a plasma cloud. Some of that charge will go to the dust or the boulders of the ring and get captured, and those charges that are captured follow Kepler orbit, as opposed to the uncaptured part of the plasma cloud follow co-rotation. If you separate the plasma from one sign of charge from the other, you build up in azimuthal electric field. If you have an azimuthal electric field, my goodness, and you have a gradient in the magnetic field, that whole plasma would drift radially out. As the plasma drifts radially out, it can pick up dirt, and what we see in spokes, how spokes propagate, is not that any of the dust particles would move large distances in radius, but the vacuum cleaner above it, the plasma cloud, is drifting in radius and picks up new dust as it travels. That's a wonderful model. Whether it works or not, the jury is out, but there is another caveat to this, because to maintain that electric field, you have to make sure that the currents that you could send up and down along magnetic field lines will not short this electric field. If you short the electric field, the story is over. The cloud will propagate nowhere. So what happens to those currents really is decided at the resistivity, at the footprint of those field lines. If the resistivity is high, you will maintain the electric field. The plasma cloud will propagate. If the electric field is low, if the electric field is high, you propagate. If you short it, you stop. So let's take a look. Why would then the morning terminator be preferred if you have impacts probably all around? That is preferred because look at the footprint of these field lines would still map into the dark. When sun is shining, you maintain the ionosphere. You produce a whole lot of electrons and ions. Your conductivity is high. You would short that electric field. So the most opportune time to map the field lines where the hit happened and to maintain a large electric field in the ionosphere would be the morning part, where the conductivity in the ionosphere is the lowest. So, of course, the story is changing as Saturn moves around the sun. And this is just a history of the observations when spokes were seen. And that is the tilt angle of the sun with respect to the ring plane as time goes on. Voyager 1, Voyager 2 have seen the spokes. We had a ground-based Hubble Space Telescope series of observations that have seen the spokes all the way until this tilt angle became about 20 degrees, and then the spokes vanished. People argued that, it has to do with the line of sight and optics and whatnot. Wait until Cassini gets there, and Cassini got there, and there was not a single spoke for a whole year. They were gone. And of course, they reappeared in the fall of 2005. Cassini took a 90-degree turn and went into the ring plane when, not a 90-degree turn, but it was very close to the ring plane, and it couldn't make observations, but now we do see spokes, and they are there. So I would like to stop here, and I will tell you what we think would happen. Is that true? No, that's where I will stop. The reason they vanish and don't vanish is the background plasma. When the sun is shining at a large angle, you produce a lot of photoelectrons, and the background plasma kills off the process that would maintain this large electric field. When the tilt angle is somewhat smaller, then the impact plasma is high enough to overrun the effects of the photoelectrons produced from the ring, and the spokes are running. So it's a seasonal phenomenon. Spokes are turning on and off depending on the tilt angle of the rings. So I would like to stop and give you a break.